In this session, we will be discussing a few questions from Floyd chapter 6. Question number 1. What are the half-adder inputs that will produce the following output? So the first, there are many parts for this question, but I will be answering part A, and the rest will be similar, same spirit. Before we answer that, let's recall how we do binary addition with two inputs. So we have, when adding 0 plus 0, the result is 0. 0 plus 1 is equal to 1. And 1 plus 0 is equal to 1. And finally, 1 plus 1 is 2. How we write 2 in binary? We write it as 1, 0. So this is the sum. This is the sigma here. And the most significant bit is the carry. Okay, the truth table expresses this idea here. So 0 plus 0 is 0. We can say 0, 1, 0, 0. 0 plus 1, this is the second case. Okay, this is 0, 1. It means the carry is 0. And this is the third. This is equivalent to this part. And the final combination, when both inputs are 1, we have this. Okay, now to answer the question, we just need to look at the output. This is the input. This is the output. Just we need to find the row when we have the sum and the carry are both 0. So this corresponds to the first row. Then the answer will be this. So A must equal to B and both equal to 0. Next question. For the parallel adder in figure 667, determine the complete sum by analysis of logical operations of the circuit. Verify your result by longhand addition of the T input numbers. Okay, so we have here 1, 2, 3 full adder, and the full adder, as we know, work by adding the input. All right, they add the input, the first, the second, plus the carry in, and produce the sum here. And if there is a carry, then the carry will be propagated through this line for the next phase. All right, let's do this. So we have here 1 plus 1 and plus the carry in 0. So this is just 2, 1, 0. So this means we're gonna have here 1, 0, and this guy here we're gonna be propagated, will be here. All right. So now we have what? We have 1 plus 0 plus 1. I'm just rewriting these. Okay. So again we have 1, just 1 plus 0 plus 1 is just 2. Again 1, 0. So the result will be here 0, and we have a carry here. One more time. So the final step, we have 1 plus 1 plus 1. For this one, just we're going to make it easier by dividing the addition into two parts. So first of all, I'm going to add 1 plus 1, which is going to give me 2, which is 1, 0. All right, and then I'm going to add to that 1. Okay, or I'm going to write it this way in a familiar way. So this is 1 plus 0 is 1, and 1 plus 0 is 1. So we have this value. This is 1, 1, 0, 0. Remember how we read the binary number. We read them from the most significant bit. 1, 1, 0, 0. Okay, so this is the result. And the second part asking us to do the addition. So we're going to do that. We're going to write them in a familiar way. So I'm going to collect the A's, right? So the A's, you see them all ones. So 1, 1, 1. and the B's we have 1 0 1 1 0 1, and then I'm going to carry out the addition. So 1 plus 1 is 0, and I have a carry here. 1 plus 1 is 2, so I have here 1, and I have 0 as a result, so 0 plus 0 is 0, and we know from the example here, then we're going to get 1 1. We're going to verify this 1 1 1 1 1, all this is just 7, okay, and this the second operand is 5, so when we add these two numbers we get 12, so it's better this one be 12. Let's check. So a shorthand for conversion is to look at the ones we ignore the 0. So I'm gonna take this one, I'm gonna write it here, I'm gonna write 2 and count how many digit to its right. We have 2, right? I'm gonna write this second, get another 2 here because it is 1, and how many digit in front of it? 3. And then I do the addition. I know this one is 2 times 2 times 2, this is just 8, and this is 2 times 2 is 4. All right, so indeed this is 12. Okay, and this verify the answer. And the final questions says, when a law is on the output of its decoding gates in figure 675, what is the binary code appearing on the input? And the most significant bit is a 3. Okay, so this question is about decoders, and you recall decoders are circuits. Their job is to detect some messages, some input. So we are looking about what as a decoder, this circuit will indicate what is the situation on the input. So this is the input. So the question here is talking about the law. All right, when the output, this is the output when it is low, meaning when it is 0. All right, and the answer is simply all combinations. What I mean by all combination, since we have 4 input, then we know that the number of possible messages will be 2 to the 4, which is 16 of them. So since the output, we are concerned about the law, then there must be some 15 messages. Any of 15 messages will generate law. The only time when we're gonna have high is when we have a 3. Let me write them here. A 2, a 0. The only time when the output will be high is this 1 1 1 0. So this is the exception. So the question is asking, what is the exception? What is the exception that it is like this circuit exclude this kind of combination? So what this mean? It means if I put them all 0, will do. Let's see. If I put them on 0, then will be this 1, and this is 0 0 0, and this, because this is an AND operation, then there will be low. So anything will do. The only situation where the output will be high is this guy. Let's see how that works. When this one is 0, it's going to be 1, and here's 1, all of them 1, then the result will be 1. So, and this gives us an answer to the question where we have the same statement, but instead of this, somebody says, talking about the high. Okay, what make it high? Then our answer will be make all the input 1 except the least significant, except A0, make it into a 0. I'm gonna leave the rest as exercise, but basically the same idea, no difference.